I pose this sketching task to you and will give you a moment to sketch this out on a scrap piece of paper. I use the sketching task as a segue into the reasoning of this proof on the screen. So what do you think of the proof? I'm going to give you a few minutes to think about it. Turns out there is nothing wrong with this proof. The chain of reasoning is fine and the conclusion must follow if the figure is correct. But this fallacious proof, according to King and Schatzschneider 1997, has been around for over 100 years. And maybe some of you have already seen it. Some have used such proofs as a way of banning the drawing of any figures. However, I'm sure all of you will agree, as I have with King and Schatzschneider, that such examples offer really solid reasons as to why we should be emphasizing the need for accurately constructed figures, especially in deductive geometry questions. Careful constructions that went beyond shoddy geometry sets lent itself to the use of dynamic geometry software. If you look at Wikipedia, which I'm not saying is the be-all and end-all of all respectable sources of information, I was surprised at how many dynamic geometry environments are actually out there now. It is one of the links on my reference list if you'd like to explore it. Dynamic geometry environments have been around for a while now. We're talking the early 80s. But these are the ones that stuck in Math Ed. Sketchpad. Sketchpad began as an offshoot of the Visual Geometry Project VGP at Swarthmore College, directed by Eugene Glotz and Doris Schatzschneider. In the mid-1980s, the project proposed the development of a videotape series that would focus on three-dimensional geometry, but this became all too difficult, and thus was born Geometry Sketchpad. What are the affordances of Sketchpad and other such dynamic geometry environments? Obviously, there's accuracy, bearing in mind tolerances of the internal computation of whatever device you're using, but visualization is one of the key ones. It helps students build mental constructs that are useful for analytical thinking. There is exploration and discovery, which allows for that surprise factor and expects students to dig a little deeper. Proof? Well, while it cannot actually produce proofs, there are many research studies that show that students are able to transcend the technology and devise proofs. Thus, dynamic geometry environments are a motivating factor. Transformations. Students can see that functions are not simply synonymous with symbolic formulae. Loci. Knowing that a point that is equidistant to another point and a line is not quite intuitive and hard to imagine. Finally, simulation and microworlds. Yes, we have this fantastic tool that does all of these things, but what do we know about how students learn geometry? The Van Healy levels of understanding are a widely accepted model of how students learn geometry. Level 1 is where a student identifies shapes and figures according to their appearance. So, that is a square. Whereas level 2 students identify shapes according to their properties. For example, a student might think of a square as a figure with 4 equal sides. Level 3 students might identify relationships between sets of figures. For example, describing a square as a special form of parallelogram because it has opposite sides which are equal and parallel. Students develop a sequence of statements to justify a conclusion. They understand that deduction is a way of proving geometrical results at level 4. And finally, at level 5, students are able to comprehend new geometry systems. But all this is well and good. Research shows that there is a need to promote student-centered tasks, investigative tasks, that go beyond verifying a geometrical fact or demonstrating a geometrical property using dynamic geometry software. We now have a powerful technology and the knowledge of how students learn geometry, as well as what sorts of tasks best promote the kind of understanding that we all desire for our students. But there is the role of the teacher that really brings all this together, and for the vast majority of teachers, simply having access to the technology is not enough for them to successfully integrate dynamic geometry environments in their classroom. Standards such as the Common Core State Standards in Mathematics and education policy definitely impact the uptake of technology such as dynamic geometry software. The school as a whole does so, and so does the math department, and how they function as a community would very much influence a teacher's uptake of dynamic geometry software. The availability of resources, whether it's the actual technology hardware or the content attached to the dynamic geometry software in terms of tasks and activities. The teacher's technological, pedagogical, mathematical knowledge, which is often influenced by professional development. And finally, the teacher's beliefs about the role of technology would all influence the uptake of technology such as dynamic geometry software.